Hello guys, this is lesson 5 of Decision Mathematics, where we will start chapter 3 that will deal with the algorithms on graph, that means specific algorithms, and I'll split this section to two parts. As you can see, the last point that is included in your book is not included in your syllabus. That's Floyd's algorithm you can skip. So we will talk first section or first video, lesson 5, we will talk about the Kruskal and Prim's algorithm. And in lesson 6, we will apply the Prim's algorithm to distance metrics and use the Dijkstra algorithm to find the shortest path between two vertices in a network. So today we will only focus on these 2 points, Kruskal's and Prim's algorithm. The first one that we start with is the Kruskal algorithm. Both of them produce the same things, is the minimum spanning tree. You can recall from the section before, from lesson 4, what the minimum or spanning tree is. And the minimum spanning tree will be the tree where the total length of its arc is as small as possible. That means it connects all the vertices with the shortest possible sum of the distances between them. That means find, like in reality, in real problems, it finds oftentimes shortest or cheapest or the fastest way how to link either some cities or some points of interest into one system. The algorithm works like this. If you are given some network, so you need to sort the arcs or the edges into ascending order of the weight. That means from the minimum to maximum. Then you will start your tree with the smallest or the shortest edge between the vertices. And then the next one that you will add to the tree is the one that is again the shortest possible, but that doesn't form the cycle. If it does form the cycle, you skip it. And then you choose the next one possible. And then you keep repeating these steps until all vertices are connected. I think it's much easier when you will see how it works. So let's do a couple of the problems. So let's look at example 1. We are given this network. So the first thing what the algorithm tells us to do is to order the arcs or edges according to their weight. So by inspection you can see I will order them, or I did order them based on their weight, DE, AE, BC. These two have the same weight, so it doesn't matter which one you will place first. The same is true for AD and BD. They too have the same weight. So because the DE is the shortest one, I am adding the DE or ED to my tree. The next one, because the DE was added already, the next one is AE, which I added here with the green one, taken from the book. I could also choose BC. Okay, so you can do that one as well. Then, because these two were added, and the next one is BC, and it doesn't form the cycle, I can do that one as well. So all 3 would be there. And then the next ones, because these 3 we have already, the next one, the shortest one is AD. That was not added for the reason because if I add it there would be the cycle like this. So that's why I can skip that one and I can reject it. Okay, I don't need to, I can delete this one because the reason why it would create the cycle, so I can skip it and reject it. And that's why I added BD instead. And I am finished here because all of my vertices were connected. And because I always added the shortest edge, that means the spanning tree that I created has the minimum weight. The weight can be easily found as when you add the weight on each edge that created or that was connected or was added to the spanning tree. So in this case, it's 20. So if the weight on the edge represent the distance, it's 20, let's say, kilometers or meters. If it represents the time, let's say in hours, then it's hours. So the next question, example number 2, is asking us to do the same. So I have, in this case, I have 6 vertices, and I need to create the minimum spanning tree for this network. So the first thing what I'm going to do, again by inspection, that means by looking at it, you will order the arcs. So in this case you will have the length of 8, you have 2 arcs, and the same is true for length of 10 and length of 12. And then you start with the shortest one. So I order them like this so I can see them, and then I will keep adding it. So AD is there, it's the shortest one, and then I can add BC as well, because it's also the same weight of 8 and doesn't form the cycle. The next one you're going to add is AC, and you move on to CD, but this one is not going to be added there because it would create the cycle. If I would add it here, then I have a cycle there, so I can skip it. And next after CD is EF. That is completely fine here because it doesn't create any cycle, any problem. And the next one after EF is CE, and that also is fine. And that also means that I'm already finished because every single vertex was already connected. So all I need to do is to state the weight of this network or of this minimum spanning tree, and that means I just need to add the weights of the edges that were added to this minimum spanning tree. So 8 plus 8, 10, 11, 12, together it's 49. The second part of that question is we need to show there are 4 minimum spanning trees for this network and also state their weights. You could notice at the very beginning, because I had 2 edges of the weight of 8 and then 2 edges of 10 and 2 edges of 12, you can notice because you can choose either CE or DE, and you can choose either AC or CD. That means your tree is not unique and you can create different combinations. So the 3 other solutions are offered here, and as for their weight, they always have to be the same. Even if the minimum spanning tree is not unique, the weight of that minimum spanning tree must always be the same. But because I am choosing or I'm using the edges of the same weight, so when I add them, obviously I have to get the same sum, and that sum is the minimum possible. So now again, I'll ask you to practice on your own while I'll guide you. So you have 2 options: either pause the video and then later double check if you got the same answer, or if it's still not really clear to you how it works and so on, then you can watch the whole process. So in this example, we are given the network and we are asked to find again the minimum spanning tree, state the order in which you included arcs. This is always very important. At the end, we need to draw it and we need to state the length. So we're going to first start with the smallest or the shortest possible edge, and that in this case is BH. Be reminded that the network doesn't have to be drawn to scale, so that means you don't worry about the length of the edge, but about its weight that is stated by the number above. So the shortest possible is number 5, that is BH, and I can add it to my network because it's the first one possible. So this one is added, so I put a circle around that one. Next one is 6, that is NF, that is also added there, so I count this one. The next one is 7, that's fine, the cycle is not created, that means it can be added there. Next one is 8, HA, that is also alright. Next one is BE. BE is number 9, I mean it has the weight of 9. And the next one is 10. What is NA? But when you look at it, I cannot add it to my 3, so I can cancel it or reject it because it would create a cycle. So just skip it. I am not counting that one because the cycle would be created. The next one is EF, but that also would create a trouble and the cycle would be created, so I cannot add it there either. So I can reject that one as well. Next edge is FA, 11. FA cannot be added there for the same reasons. And next one is EH, and EH also cannot be there, so I can skip that one too. Next possible one is CN, what has the weight of 13, and that's at the same time the last edge I needed to add, because then I have my minimum spanning tree finished, because all of the vertices are connected. Now I can count the length or the minimum length or the length of the minimum spanning tree, and I just add all the numbers or the weights of the edges that were added there. So 5, 9 is 14, 8, 22, 7, 29, 35 plus 13 is 48. Example 4, we have very similar when you look at this network and network from previous case. They are exactly the same except the weights are multiplied by 10. And this network models a car park. There are 2 pay stations at the E vertex and N vertex. These 2 are linked by a cable as shown. So this black, the thick black arrow represent this link. The new pay stations are to be installed at B, H, then A, F, and C. The number on each arc represents the distance between the pay stations in meters, and all of the pay stations need to be connected by cables, either directly or indirectly. The current cable between E and N must be included in the final network. And now, obviously, we want to minimize the cost of the cable used, so that's why I am looking for minimum spanning tree, minimum amount of new cable. We need to use, or do it otherwise, but it's good to use the answers to part example 3 when we can determine the minimum amount of the new cable. So we can use the diagram that we found in example 3, and now we can decide how to find out. As I know, the length of the minimum spanning tree is 480. That would be usually given. If not, you would just have to add manually all the weights for every single edge. But what I know is that EN must be included in the final network. That gives me the chance to disconnect HN or BH or BE. One of these must be removed in order to cancel the cycle that would be created, since the red one, the EN, must be included. And obviously, if you want to get the minimum, you have to remove the longest one. So from BH, BE, and HN, HN, the longest one is BE. That's why I am removing longest BE, what is minus 90. So the new cable that would be needed is 390 meters. Now let's look at example 5. The story is exactly the same, except I don't have the animation available for this one, so we're going to do it on our own. The first thing what we need to do is to order the arcs, and I'm going to redraw A, B, C, A, B, C, then I have D and E. I'm going to delete this one. Then I have F here, then I have G, and then I have H. So I'm going to order them, or you can identify the shortest one would be EF, that is this one. So EF is the first one, that's 11, and you can connect E and F. Then the next one is BD. BD is 12. So this one, BD, size 12, B and D are here. Then next one is CD. CD is here, 12 again. Of course, you could switch them. CD, I still can edit there because there is no cycle. The next one is number 14, that's this one, AH, AH 14. AH is fine. Next one is DF 15, DF 15, D and F, that's all right. Next one is AC, that's 16, AC 16, it's still fine. Then I have next one is BC, but be careful here because here the cycle would be created, so I can skip that one. You can either say reject, or do not even include it. And then I have next one is 18, what is GH or AG, AG 18, and that means it's finished. You also had options for the BE, but that would create a cycle. So you could either reject this one and add HH or HG, or you can just switch them. So add HG first and reject the rest of them because you are finished actually. Reject the rest. How do I know I'm finished? Because I connected every single vertex. And how do I know it's a correct one? Because I don't have any cycle. Okay. So when you look at the example 6, it has several parts, and part A or case A has something to do with the definitions. And this is very important to notice, even when you will start to practice the released papers or release problems, you will notice in some questions they will want from you nothing else, just to define the terms precisely. So in this case, we can write it here, and you have to go back in your mind, in your memory, and in your understanding, back to lesson 4, to the previous one, when we introduce all of the vocab that is necessary while working with the graphs, and recall what is a tree, and then you will just write the answer on the paper on the exam. So if you can recall, tree is a connected graph where there are no cycles. And then minimum spanning tree is obviously a tree where the sum of the weights of the edges that connects all possible vertices is as minimum as possible or smallest as possible. So it's definitely a tree. Minimum spanning tree is a tree. where or with the minimum total weight of edges which connect all vertices. So B, C, and D I will do on the next slide. So I have the B case here. We need to find the minimum spanning tree and we need to draw it. So in here I'm going to write the edges in order. So in this case I have the shortest one. By inspection you can go. So I have YZ, that is 15. Then the next one is 16 VW. Then next one is 17 XY. But I have another 17 UW. The next one is 18, what is UX? And SU. Then I have one more 18, no, two more 18. I have VX, WX, and I also have WZ, it's the same weight. Then I have UV, that is 19. Then it's 20 UT. Then it's 22 ST. And then it's TV or VT 23. So because I need to draw it, I would redraw STU. You will be given these pictures on the paper on your exam, so you don't have to redraw it and lose the time. And then I'm going following the algorithm says at I'm going to choose a different color, at the shortest, so YZ is the shortest one that's included. Then I have VW, XY, that's fine. UW, that's also fine still. UX, that's all right. SU, that's fine. WX I cannot, so I can reject this one because it would create a cycle here. Okay, I don't want to draw it, but you can see directly here. And then WZ, that would also create a cycle, so reject that one as well. And then I have UV, that's also create a cycle. And then I have UT, and that's fine. That is fine, UT here. So UT is the 20, yes, that's fine. So I have a C case completed as well. And now you need to state with the reason whether the spanning tree that you found is the unique one or not. And obviously, because you could see the while you ordered the arcs, you could see that the tree is not going to be unique because you have several edges that have the same weight, and maybe in some cases they could be replaced. For example, when you look at UX that we included, UX is here, I could replace it with WX. So WX would be here, but I would delete this one then. But the weight would not change because both of them are 18 and 18. Okay, so it's not unique. It's not unique. This is the answer, but the reason is important. You cannot forget to include it because, for example, UX could be replaced with WX. Have the same weight. Okay, we didn't mention the total weight, so the weight of minimum spanning 3 is equals to, just add all of the weights or weights of all of the edges that we included. If I'm not mistaken, I got 121, so you can double check. So let's move to the second point of today's lesson, and that's the Prim's algorithm. That is also creating or finding a minimum spanning 3, but does it a little bit differently. While the Kruskal algorithm starts with the shortest edge, the Prim's algorithm starts with any vertex. Usually in the question itself, it tells you which vertex to start, so they can, create a mark scheme for it. But if it doesn't state, then you can choose any vertex you like. After you choose the vertex that you start your tree with, you select an arc of the least weight that joins a vertex already in the tree to a vertex that is not in the tree yet. And obviously, if you have a choice of two arcs or two edges of the same weight, then you can choose any. So let's look at it, how it works, because you need to repeat these steps, obviously, until all of the vertices are not connected. So when we look at the example 7, it's asking you to use the Prime algorithm. This is very important to pay attention to. You need to know the differences between the Kruskal and Primes, because if on the exam they ask you to use the Kruskal and you will use the Prime, then you will not receive any mark or just minimum marks possible. So we're going to follow the Prime's algorithm. As the question doesn't mention any vertex that we need to start with, we can choose, and I'm going to choose the vertex A. So again, on your exam, you would be given the picture of the vertices that you can use to create the minimum spanning tree. I'm just going to redraw it quickly, D and C. So since I'm starting with the A vertex, I'm choosing the short possible edge that goes to this vertex. That means it's AF and the weight is 8. So AF is there. Then the next one, I am looking at F and A, and I'm trying to connect them with the next vertex that is not included in the tree yet. That means in this case, I have a choice between AB and AD. So I'm gonna choose one of them. In here I have chosen AB, but you could also choose AD. And I'm choosing the next vertex, again, the one that is not connected yet. That means I have a choice C, D, E. And in here you can see the shortest one possible is AD. And don't forget to record the arc that you have chosen. Now I have a choice between C and E. I need to connect these, and I can do it either through 10 or through 8, or then I have option 12, 11 and 14. So obviously the shortest one possible is CD, and that's the 8. CD, that's 8. And then the last one, I need to connect the E vertex, and the shortest possible edge there is 11. So AE, and that's 11. So the list that they asked me for is here. The weight, they didn't ask me, but I will state it. Weight of minimum spanning 3 is equals to 18, 26, 34, 45, if I didn't do some mistake in the addition. As you could have noticed in example 7 already, there are some differences when you are finding the minimum spanning tree using the Kruskal algorithm or Prim's algorithm. I will list several of them, and later when we will practice in the guided practice, I'll show you, we will do maybe 2 examples, the animated version that you can see on one screen when I'll do it with the Kruskal and Prim's algorithm. If you want, stop the video now and try to think if you could observe at least 1 or 2 differences on your own. So the first difference that you could observe is that while in Kruskal algorithm you start with the shortest edge, in the Prim's algorithm you start with any vertex. The next one, what you could notice, in the Kruskal algorithm, the tree grows in a way that the edges are jumping around. Okay, tree grows in a way that the edges are jumping around. While in the Prim's algorithm, you could notice it grows very smoothly in the connected way. Grows in a connected fashion, very smoothly. Then next one could be that in Kruskal you need to check for cycles. You need to check for cycles. And in the Prime algorithm you don't need to. No need to check cycles. Some of you could ask already why is it so, and also you could notice the difference lies in the fact that in the Kruskal algorithm the shortest edge is added, or the shortest arc is added, unless it obviously create or complete cycle, unless it creates cycle. While in the Prim's algorithm, the nearest unattached vertex is added. Nearest unattached. In example 9, as I mentioned, some of you might already wondered why there is no need to check for a cycle when using a Prime algorithm. When you think about it, you are always adding a vertex that is not in the tree yet, because you're always adding the nearest possible vertex that is not connected in the tree. That's why the cycle cannot be created, because the vertex you are adding is not in the tree. And that's the reason why there is no need to check for cycles in the Prim's algorithm. So I'll just write down what has been said. In Prim's algorithm, the nearest vertex So let's look at the guided practice. I prepared a couple of the questions. So do you remember this example from the Kruskal algorithm that we have done? It's exactly the same network, except we need to use the prime algorithm now. In this case, they tell us to start with the vertex A. Okay, so that's mean it's here. So I'm going to redraw it. A, B, C, D, E, F, G, H. So since I'm starting from A, the shortest possible one is AH. Do not forget to record your the list of the to list the order of the arcs, because it's very difficult to recover it once you are finished with the whole tree. So now I have AH, so I'm looking for the vertex that I can connect, and it's easy because I don't have to look at B, E, F or D. I'm just looking at the neighbors. So AB is 25, AC 16, then I have 20, and then I have 18, so obviously AC is the shortest one. So AC 16. Then I have the next one is 12, CD. Then I have 12 again, DB. Then I have 15, that's probably it, 15, DF. And then I have 11, FE. And the last one is HG, that's 18. So that's the weight of the minimum spanning tree. So when you add it, this is 30, 42, 54, 69, 80, and if I'm not mistaken, should be 98. Okay, and for this you would get a full mark because you have the proper picture, you have the order in which you edit the arcs or the vertices, and then you also stated the weight of this minimum spanning tree. I'll give you the chance to practice both of the algorithms on the same network, so we can also closely observe the differences between these two algorithms that we talked about a couple of minutes ago. On this network, in example 11, starting with the primes algorithm, they ask us to start from vertex A. So if you want, again, you can pause the video and you can compare later your answers, or you can follow if you need or if you feel unsure. So I'm starting from vertex A. That means the shortest one is shortest, or the nearest vertex is E. That means AE would be the next one. Then EF is the next vertex that is the nearest to already connected A and E. Now I have AE and F, so I'm looking for the shortest connection, that is 20, then it's 24, 14, 12, so 12, so that means I'm going to connect J with 12. Then I have the next nearest connection would be I, that's 20, that's this one. Then I have 14, 24, so 14 would be the next one, IG. Then there is a 17, 18, and 26, 24, so 17 is the next one, that's GC. Then 9 is D. And that gives me one more, no, two more I need to connect. That's a B and K and H. So B I can connect with 19. Then I can connect K through 24. And then I can connect 22H. So the minimum weight of this 3 is 172 when you add them together. And then when we're going to look at the Kruskal algorithm, we know we need to order the edges from the shortest to the biggest one and keep adding them in this order unless they create a cycle. So EF, that's the shortest one in this case. Then the next shortest one is, let me see, 12, 9, so CD. So you can notice here, while the prime algorithm, the tree grows in the connected fashion, in here the edges are jumping around before they get connected. So 9. Then the next bigger number is 12, so EJ. Then the next one, I have two 14s. I cannot add JF because that would create a cycle, but I can connect IG because there is no cycle. Then I have GC, that's 17. So the next one is 18 GD, but I can't connect that one because that would create a cycle. So I can go to 19 and that's BC. And after that I have 20, which is fine because no cycle created. And then it's 22, that's HK. Again, you can see jumping edge. Then it's 22. And then it's 24 that will connect K. I also have another option that's FC, but that can't be added because it would create a cycle. So 26KJ cannot be added because again cycle. So then I have 27, that's AE. And that's basically finish my tree because all of the vertices are now connected. The minimum spanning tree has the length 172. So in example 12 we have the same situation, except in this case they ask us to start from vertex L in case we're going to do the prime algorithm. So when we look at that, from the L the nearest vertex is T, so that means it's 3.8. Then I have from L and T are already connected, so the shortest or the nearest next vertex would be 4,1. That means M vertex, so TM is the next edge. That means it will connect the M vertex to my tree, it will add it there. Then I have 3,7, that's the Q. Then from these 4 vertices, the next one that is the nearest one would be 4.7, that means n. And next one is 6.6. I have 2 options. I can either add R or I can add S. So ST and QR both has S, and the only one that I'm still missing is P, and obviously the shortest edge is NP, so I'm adding it there. In the Kruskal algorithm, you know we need to start from the shortest edge. That means I would recommend you to list the arcs in order first, but you can also do it directly from the network. Just do not forget to list the order in which you were adding the arcs. So in this case, the shortest one that we start with is MQ, what is 3.7. Then the next shortest one is LT, what is 3.8. The next number that is the next weight is 4.1, what is TM. Then after that one is 4.7, QN. Then I have 5.3, but I cannot add that one because that would create the cycle, so I can skip that one. The next one is ST, what is 6.6, but I have 2 options there. I could also do QR, that I still can add because there is no cycle. And then I'm still missing P vertex, what is 6.8, obviously it's the shorter option, so NP. And this is all for today's lesson. We have covered both Kruskal and Prim's algorithm as well. If you have done all guided practice questions and you didn't find any trouble or everything is clear to you, then you are all good. If you do have some things that you would like to clarify and to ask about, then please come directly to tutorial, and also come if you do wish to practice more of the questions of the same type. The questions that we will do are the set 3A and set 3B, as now are on your screen. If you have time and you want to do them ahead and do not want to come to tutorial then there is this option. You have the solutions and answers at the end of the book, and of course also detailed solutions are online. If you do need any kind of support or you wish to practice more with me, then please come to tutorial.